Hello, everyone. This is Jashwant here, and I'm going to be presenting my doctoral thesis, which is about pushing the performance and cost envelope for the next generation cloud platforms. So, towards this, what I try to do in my thesis is I try to solve the dual problem of cloud tenants and cloud providers, where I want to ensure low cost and high performance for the applications of cloud tenants, and at the same time, I want to ensure high utilization and energy efficiency for the cloud provider front as well. So to give you a very high level overview of the individual contributions of my thesis. So if we take cloud computing, for example, it tries to there are a lot of applications which are executed by tenants at cloud nowadays. And I mostly focus on the machine learning based applications. The reason being that they are going to have a very fair market share in the future, and they are projected to have about 43% compounded annual growth. So these applications, when run on cloud, what you need to do is that there are a lot of resources to rent and choose from. For example, I have different kinds of virtual machines, platform package solutions, or even function as a service solutions like serverless functions, right? So from the so many options available, cloud tenants need to do this tedious task of selecting the resources which they want to run, scale these resources based on demand, and then make sure that applications are mapped well onto these resources. All of them play a very important role on the cost, latency, and performance for the application. And my first contribution in this thesis tries to address the cost and latency problem. So more specifically, I try to see that how the more recently emergent serverless functions can be used in a way to efficiently auto scale by having minimal latency violations, and at the same time not to increase the deployment cost. And the next part of my work tries to dive a bit more deeper into the application. So here I focus on machine learning inference application, where the performance is based on the latency and accuracy of the inference requests. So here I try to optimize the latency accuracy under a low cost when they are hosted on a public cloud platform. Now, when I go towards the cloud provider front, all of this entire application stack is typically hosted on physical servers on a virtualized runtime. And cloud providers typically have a resource management layer in order to do the container packing, the virtual machine spawning, scheduling, and whatnot, right? Which in turn have an effect on the power, energy, and utilization of their data centers. So more recently, with the introduction of serverless functions, a lot of the management overheads have gone to the cloud provider from the cloud tenant. So the third part of my thesis tries to improve utilization and the energy efficiency for specifically for serverless platform providers. So now let's take a dive into some of the high level contributions of each of these individual perks in my thesis. The main application I target is model serving, which means that there are a lot of applications which use machine learning models like image classification, NLP, etc. So these will have a pre-trained machine learning model which is being hosted on hosted as a web service, and they will be typically hosted with the resources like virtual machines, containers, or serverless functions. And typically the users send requests and get a response back, and they have a very tight latency requirement, which is usually within 1 or 1.5 seconds, the overall end-to-end response latency. But these resource provisioning time play a very high role, especially when I'm trying to scale up resources to meet the user demand. And typically the provisioning time for virtual machines are in the order of tens of seconds more than the execution time of these inference requests. So what a lot of these prior work try to do is they try to scale virtual machines based on trying to predict the request rate, or trying to scale them based on increased CPU usage or increased memory usage. But all of these solutions, they typically deemed to be largely expensive. So what I try to do in this work is I try to focus on serverless computing, wherein I can just scale functions instantaneously, and it's going to remove a lot of the management overheads of scaling from the user. But just using serverless functions as a replacement for virtual machines was not the solution, because even that seemed to be expensive. So what I try to do in my first work, Spark, is that I try to use serverless functions as a handoff when I'm trying to spin up new virtual machines on demand. So if you can see here, when I'm trying to scale the number of VMs due to the increase in the request rate, I try to use serverless functions as an efficient handoff mechanism. So this in turn, it led to around 74% reduction in SLO violations compared to PM only solutions, and I was able to reduce the cost of just using PMs. So in this work, we try to use both VMs and serverless functions in a union to satisfy SLO guarantees at a low cost. Now, as I told in model serving applications, besides the resource provisioning latency, which I solved in Spark, the time taken to run the inference model and the accuracy of the model also play a very important role. Because even if you take in the case of Netflix, how accurately you give them predictions is extremely important. But if you take an example here for running an image classification application that I show the accuracy on the left axis, the latency on the right hand side, it can be seen that there is a lot of variation and you have a lot of options to choose from these individual deep learning models which can do an image classification. So how the prior work tries to give you improved accuracy at a low cost, I try to more specifically focus on two important works, which are infas and clipper. So here I plot the cost, latency, and the accuracy trade-offs for both infas and clipper. It can be seen that infas has a lower cost, but at the same time it is bound by the accuracy offered by individual single models. Whereas Clipper, on the other hand, has higher cost, reason being it can do an ensemble of ML models to give a single inference request. And by doing ensembling, they can increase accuracy, reduce latency, but the cost goes high. So what I try to do in this work is to take the ensemble learning approach, try to reduce the cost of ensembling, at the same time give me high accuracy under a low latency. So in order to reduce the cost, we kind of take a two-pronged approach. The first approach is to develop a dynamic model selection policy, which can try to leverage the information about the image classes which I'm going to infer for, and then apply a weighted model selection there in order to reduce number of models used in per ensemble. And at the same time, when these requests are going to be hosted on public cloud resources like virtual machines, we try to use proactive prediction policies to predict request rate and use dedicated pool of VMs for every individual models. And at the same time, we try to leverage these transient VMs called like spot virtual machines, which are around 60 to 70% cheaper compared to normal VMs. So these virtual machines in turn can be revoked or fail at any time. But since I use a distributed approach of using dedicated pools for individual models in the ensemble, it kind of becomes inherently fault tolerant even when some of the instances can be revoked, because ensembling by nature, if it's run in parallel, it is more fault tolerant than just running a single model for doing an inference. So by doing this, Cocktail was able to achieve 2x lower latency with up to 1% gain in accuracy when compared to single model only approaches. At the same time, it was able to reduce cost by 20% when compared to the traditional ensemble approaches like Clipper. So now the third part of my work is to tackle the issues from the provider side, wherein if I'm going to use serverless function, let's say to host my model serving, the container management and provisioning is taken care by the cloud provider. But the main issue here is that these containers inherently come up with cold starts, which can be attributed to a lot of factors. And typically from our study, we found that cold starts can be in the range of 2 seconds all the way up to 8 seconds. And in fact, they will again contribute to the SLO of they will contribute to the end-to-end SLO of a request, because the end-to-end SLO is typically within 1 to 1.5 seconds, and these can be significant. So what happens with the current serverless platform providers, what they typically try to do is to always have a lot of containers which are provisioned in advance in order to maintain SLOs, or they try to reactively spin up more and more containers as they get more requests. All of these will inherently either lead to SLO violations from cold starts, or it can lead to an underutilization problem where you have a lot of containers, but I only have a few number of requests to run. So what we do in this work is that, we have three major findings. The three major findings is that we found that the application execution time is much smaller when compared to the container startup time. So we try to actually batch requests onto existing containers, which is what I mean by stage aware proportionate queuing, wherein we try to offline profile the execution latencies, and we try to batch more and more requests to existing containers rather than spinning up the new ones. And in case the containers are not enough, we try to reactively scale them. But as you know that reactive scaling can still lead to SLO violations from cold start, we also have another approach to do load prediction based on machine learning models and still try to provision containers in advance. So in this way, by combining reactive and proactive scaling along with batching multiple requests onto existing containers, we were able to achieve around 31% lesser energy consumption compared to traditional approaches. And I was able to spawn 20% fewer containers on average. So to give you an end-to-end summary of the three contributions I've done in my thesis, the first two works, POC and Cocktail, try to focus more on the cost, latency, and performance of hosting machine learning inference workloads from the tenant side, whereas the last task and the third task is trying to focus on the provider side, where they guarantee the application performance, but at the same time, they try to improve the energy efficiency by increasing the resource utilization of hosting serverless functions on containers. Here, I'm trying to show a very brief timeline about my entire PhD, and I'm right now looking to graduate by the end of summer. So thanks for attending my talk. And now I'm going to leave the floor open for any questions. Thank you again.